In this practical lesson, you will learn about the hybrid edge, combining SQL filters with semantic search. In production AI applications, pure semantic search is rarely sufficient. Users almost never search the entire vector space globally. Instead, they search within a specific scope, such as searching only within their own company's documents, looking for products within a price range, or filtering logs by a specific date window. When you combine traditional SQL relational filters, for example, where status is equals active, with vector distance operators like order by clause, PostgreSQL faces a critical architectural decision on how to execute the query. Let's learn about the metadata filtering dilemma. PostgreSQL handles hybrid searches using one of three execution strategies. Understanding these mechanics prevents severe production performance degradation. So let's learn about these three execution strategies. First strategy is pre-filtering using subqueries or CTs. The database first filters the metadata records using traditional B-tree indexes, creates a temporary result set, and then performs a vector search on that subset. The trap here is if the metadata filter is highly restrictive, for example, matching only 50 rows out of 10 million rows, an approximate nearest neighbor vector index like HNSW cannot be effectively leveraged on the tiny subresult, forcing a fallback to a slow sequential scan on those 50 rows. The second execution strategy is post-filtering, that is through standard SQL execution. The database uses an ANN index using HNSW or IVF flat index to find the top k globally closest vectors and then discards any results that do not match the metadata where clauses. The trap, the recall ghost. If your vector search fetches the top 100 global matches, but 99 of them belong to a different tenant, your query returns only one valid result instead of the requested 100. This drastically breaks your application's search recall. The third execution strategy is single stage in-index filtering. This is the modern solution. PostgreSQL utilizes modern pgvector iterative index scans. As the HNSW graph is traversed, the engine dynamically evaluates the relational constraints directly on the index nodes. If a node fails the metadata check, the graph traversal algorithm bypasses it in real time, scanning until it satisfies both the vector limit and the structural filters. Let's learn about the execution strategy comparison between pre-filtering, post-filtering, and in-index filtering. How this execution strategy works, what are the primary risks, and what are the best use cases. So as you can see, pre-filtering works with relational index filter KNN scan. The primary risk is high CPU slow scan on tiny subsets. Best use case is broad categories containing millions of matching rows. Post filtering works with vector index scan, filter out mismatches. The primary risk is highly erratic result counts with empty results. Best use case, highly global data with rare filtering needs. In-index filtering works with simultaneous graph work and tuple visibility validation. Primary risk is slight overhead per index node evaluated. Best use cases, enterprise, multi-tenant SaaS applications. The power of partial indexes for multi-tenancy. For enterprise scale, the most bulletproof optimization technique for hybrid search is the partial vector index. If your application architecture filters heavily by a static partition key like an organizational ID or an account status, you can construct an HNSW index restricted strictly to that subset. This completely removes the metadata filter overhead from the runtime query plan and keeps the index entirely resident in memory. Let's do the practical task and a demo. The scenario here is you are a senior platform engineer at a multi-tenant B2B customer support platform. The support underscore tickets table holds 2 million records containing vector embeddings of consumer issues. Customers complain that the global semantic search is fast, but as soon as they restrict searches to their own enterprise account, like using account underscore ID and filter for say status equal to open, then the queries either slow down dramatically or return almost zero results due to bad post filtering heuristics. You need to implement a database schema schema that supports robust, high-speed, multi-tenant filtered semantic searches using pgvector and verify that the query planner executes an optimal in-index lookup. So the tasks that you need to perform here is create a table or schema to store multi-tenant support tickets with vector capabilities. Then write a high efficiency hybrid search query that filters by metadata before completing the vector distance evaluation. Then the last task is to implement a partial HNSW index customized for active high priority accounts to completely eliminate search latency. So let's move ahead and see the SQL statements and execute the SQL statements in pSQL command line interface. Step 1 is to enable the pgvector. So we already have it enabled. So we'll skip this activity for now. Moving on to step 2, this is to build a production grade multi-tenant table architecture. So let's create this table by the name of support underscore tickets with these columns. So let me copy these SQL statements, go to PSQL command line interface and execute this query. Okay, so this table already exists because I have created it earlier. That's fine. Let's move to the next step. The next step is to insert some entries into this support underscore tickets table schema. So let me copy these SQL statement. Let me go to PSQL and let me execute it. As you can see, 1000 records has been inserted into this table support underscore tickets. The next step is to create a composite approach using a partial HNSW index. This optimizes queries specifically targeting VIP account 101's open items. Copy this and let me go to PSQL and execute this command. As you can see, this index has now been created in PostgreSQL database and in this table support underscore tickets. Let's move to the next step here. Next step is to execute and audit the hybrid query, and we set the EF underscore search parameter to higher value to ensure high precision during structural filtering. So let's set HNSW EF underscore search parameter to value 64. Execute this command here. This is done. Then the next activity is to target query simulating a search for login issues from account 101 for the open tickets only. So this is the SQL query. So let me copy this and let me execute it here. So as you can see, our query has been executed successfully. So let's see some core best practice here. You should avoid separate subqueries or CTs for metadata filtering when performing vector searches. Write single flattened SQL queries that allow PostgreSQL to naturally trigger single stage in index filtering and leverage partial vector indexes for high frequency filter combinations to completely bypass structural overhead.